The brain is really complicated. So within a cubic millimeter of brain tissue, you might have 100,000 cells connected by 900 million connections or more. Being able to map the brain, observe what's going on in the brain, control the brain, and build brain circuits are really kind of the four pillars of what we try to do. But as often happens, the skills of neuroscience are still art forms. They're really hard to do.
MIT's Ed Boyden is using technology to map and record the brain, neuron by neuron.
Can we go into single cells, see single events of chemical communication between neurons, and really sort of eavesdrop on the building blocks of what makes the neural code what it is?
To do so, Boyden's lab is experimenting with a technique known as patch clamping.
Patch clamping is pretty much the hardest thing you can do in neuroscience. People have been patch clamping for over 3 decades, but it requires a lot of human intuition.
Traditionally, neuroscientists have performed this procedure by hand and by feel. The success of clamping onto a single brain cell depends on sharp eyes and careful hands. In the conventional approach, patch clamping is used to isolate the voice of a single cell from a choir of neurons. A scientist inserts a tiny glass pipette into the brain and then, using a microscope as a guide, clamps onto a cell membrane patch. Once attached, the pipette can collect all sorts of valuable information from the neuron.
You can do neural recordings and look at synaptic events in that cell, inject a chemical so we can see its shape, if it glows. You can actually go into a cell, harvest the contents.
But it's not enough to study one cell at a time. What if there were a way to simplify and scale up the process?
So I threw out this idea, well, why don't we try to automate patch clamping? Because that's like, the annoying thing that you spend months or years trying to learn when you begin, cellular neuroscience.
Suhasa Kothandaramaya, then a graduate student at Georgia Tech and a visiting student in Boyden's lab, started out by learning how to patch clamp the old-fashioned way, by hand.
We first went about by learning this technique for a few months and getting very proficient at it to a point where we decided, okay, we can break it down into these very discrete steps that can then be coded into an algorithm.
The first step is to hunt for neurons. The algorithm sends out electrical pulses through the pipette. When a neuron is close, it blocks its flow of electricity. The software then alerts the robot that it is approaching a cell. Once it finds a neuron, it clamps on.
We've just gotten attached to it, right? And we want to rupture the membrane to gain access to the whole cell. Yeah, it looks like we did get in, so that's exciting.
Kothandaramaya estimates that the algorithm is 50% better at finding neurons than the average human scientist. But locating individual neurons one by one is only the beginning.
If you really want to scale this technique up to a point where you're recording from tens or even hundreds of cells, you want to be able to automate this process.
Currently, the Boyden lab can measure up to 4 neurons at a time, an impossible task for a human operator. This is still not enough to understand multiple neural circuits, but it's the first step towards getting direct and complete measurements of activity throughout the brain.
It moves it away from just pattern recognition to understanding neurophysiology in a very deep way.
Patch clamping is a technique that can be used to inform and improve fields like anesthesiology. In partnership with Boyden's lab, Dr. Emery Brown is using this technology to better understand what is happening in the brain when a patient is unconscious.
Because ultimately what we'd ideally like to know is how are all the neurons in a relevant brain region behaving. That's what we'd really like to know. The auto-patching techniques that Ed has developed allow us to get some sense of that.
Brown and Boyden hope that improving their understanding will lead to insights into the complications that anesthesia causes.
What we're talking about now is just understanding how the current drugs or current processes work, but I actually believe that we could generate new processes or new approaches.
Can we develop better drugs that, for example, would have the effects of anesthesia, but maybe lose some of the side effects that occur?
Ultimately, though, their ambition is even greater. Understanding down to the neuron what the brain is doing under anesthesia could also provide insights into other brain conditions like coma, seizure, and hypothermia. Measuring 4 neurons instead of just 1 is a first glimpse into how brain circuits operate. From there, cell by cell, region by region, researchers in the operating theater and in the lab will have the tools to record how groups of neurons are behaving. This knowledge could enable a deeper understanding of consciousness and unconsciousness.